Alright, so in this video I'm going to be going over question 1 from the April exam. So, we have a diagram that shows part of a downhill ski course which starts at point A, 50 meters above level ground, and point B is 20 meters above level ground. Okay. A skier of mass 65 kilograms starts from rest at a point A, and some of the gravitational potential energy is transferred to kinetic energy. From A to B, 24% of the gravitational potential energy transferred to kinetic energy show that the velocity at B is 12 meters per second. Okay, so then we can say 0.24 times the gravitational potential energy is equal to the kinetic energy that it has. So we can substitute in the symbols here. So 0.24 times mg delta h is equal to 1/2 mv squared, and we can immediately cancel the m's here, and now we can rearrange for v. So v must be equal to 0.24 times 9.8 times the change in height, which is 50 minus 20, so that's 30 meters, and we can multiply that by 2. That gives us v squared, so we need to square root all of that. And what does that give us? Let's go to our calculator. And we have square root of 0.24 times 9.8 times 30 times 2. So now I actually need to square root on this one. So it's 11.879. Is that right? Yep, which is approximately 12 meters per second. That's important in this in these show questions. So it says here, show that the velocity at B is 12, that you give the unrounded figure first to demonstrate that you've calculated it. Okay? B, part 1. The dot on the following diagram represents the skier as she passes point B. Draw and label the vertical forces acting on the skier. Alright, so just to do this accurately, I'm going to add a ruler. And what we need to do here is show, it's moving in a circle, the skier. So the downwards force needs to be bigger than the upwards force. The downwards force is the weight force. So the downwards force is going to look like this. And this is the weight. And the upwards force, the normal reaction force, needs to be shorter. This is the normal reaction force. So this now is a correct representation of the forces, and it's clearly labeled. Alright. Part 2. So there was one mark here for getting the two arrows and forces right, and then another mark for getting the size of the arrows right, or the relative size, showing that the weight is bigger than the normal. The hill at point B has a circular shape with a radius of 20 meters. Determine whether the skier will lose contact with the ground at point B. So what this is asking is, in order for the skier to lose contact, there needs to be less than 0 normal reaction force required. In other words, the centripetal force needed needs to be bigger than the weight force. So let's work out what the centripetal force is. So Fc is equal to mv squared over r, which is 65 times the speed was about 12, and we divide that by r. The radius was 20, and so that gives 65 times 12 squared over 20, so 65 times 12 squared over 20 is 468 newtons, and Fg is mg, so that's 65 times 9.8, which is 637. And then we can say that Fg is bigger than the centripetal force needed. So skier does not lose contact with the ground. And the reason for that is that as we go faster and faster, the normal reaction force will decrease, so that she'll feel sort of lighter. She'll feel less of a push from the ground up. She will leave the ground if the normal force required gets down to 0. Then she'll feel no support force at all, and the weight force then will be providing the centripetal force. If she goes even faster than that, then the weight force is not sufficient to provide the centripetal force, and she will leave the ground. She will lose contact with the ground. The skier reaches point C with a speed of 8.2 meters per second, and she stops after a distance of 24 meters at point D. Determine the coefficient of dynamic friction between the base of the skis and the snow. Assume that the frictional force is constant and that air resistance can be neglected. Okay. So we need to first work out the acceleration here, and that will then allow us to work out what the net force on her must be. That net force is the friction force, and then we have enough information to work out the normal force, and that should allow us to work out the coefficient of dynamic friction. So just to organize our approach a little bit, we can say F friction is equal to the coefficient of dynamic friction times F normal. So we need to work out F friction and F normal. We can say F friction is equal to F net, because it's the only horizontal force acting on her during this part of the run, and that must be equal to MA. We don't know A, but we can use kinematics to work it out. Now, so we say A equals question mark, S equals 24 meters, a U is equal to 8.2 meters per second, and V equals 0 because she comes to a stop. Okay, and we'll assume A is constant or uniform. So then we need to choose the equation that is A, S, U, and V, which is this one. We go V squared equals U squared plus 2AS. V is 0, so we end up then with negative U squared over 2A. I'm sorry, we want A over 2S is equal to A, and negative U squared, so we get negative 8.2 squared over 2 times 24. Okay, so then we go 8.2 squared negative divided by 2 times 24 is negative 1.40 meters per second squared. So F friction is equal to MA, which is, and her mass was 65. 65 times negative 1.4, which is negative 91 newtons, F normal must be equal to F Hert weight, because he's on flat ground, which is mg, which we've already worked out. Have we? 65 times 9.8, we worked it out up here, 637. And so mu d must be 91 over 637. Well, negative 91 over 637, but the friction force is always in the opposite direction to the motion, so we'll just say 91 for here. So 91 over 637 gives us 0.14. 0.14, and the coefficient of dynamic friction is unitless. Okay, at the side of the course, flexible safety nets are used. Another skier of mass 76 kilograms falls normally into the safety net with speed 9.6 meters per second. Calculate the impulse required from the net to stop the skier and state an appropriate unit for your answer. So impulse is the same thing as change in momentum, which is m times delta v if the mass is constant, and in this case the skier's mass is 76 kilograms, which is not changing during this event. So we can say 76 times final minus initial, so that is, the final is 0 minus 9.6, so the impulse is 76 times 9.6 negative is 729.6. And the unit for impulse, you can have either the unit for momentum or the unit, there's an alternative unit which is Newton seconds. So this is kilogram meters per second, I'm going to say, because that's how I worked it out. But Newton seconds, oops, that looks a bit messy, let's fix that up. Kilogram meters per second. Okay, the minus sign is not required for the mark, but the correct unit gives 1 mark, and the correct calculation and answer gives another mark. We haven't rounded this correctly, so let's round it correctly. So that's equal to 730, I'm going to say negative 730 kilogram meters per second. Okay, 2 significant figures is sufficient because that's the data that was provided. Explain, with reference to change in momentum, why a flexible safety net is less likely to harm the skier than a rigid barrier. So we can use here the equation F is equal to delta P over delta T. Delta P required to stop is fixed. It's actually determined by the speed at which the skier is going when they crash, and that's not something that you can control with the barrier. And a flexible barrier means that impulse will be achieved over a longer time, and if delta T increases and delta P is fixed, the F, I'm going to change this to F average, and I'll say F average will decrease, reducing harm. Okay, so that's question 1. I'll post a second video with question 2.